Hi everyone, and welcome to this next lecture. This time we're going to group our series circuits and parallel circuits into one nice little circuit, and we call it series parallel resistor circuits. So it's got here series parallel actually looks just as it sounds. It is a mixture of resistors where some are connected in series and some are connected in parallel. So if you remember back to previous lectures, we had a simple series circuit, which meant that all those electrons had to travel through every single resistor there. That's how we know it's in series. In parallel, however, that's where we started to get these nodes where current could split up like this. So current could actually go in different directions. In a parallel circuit, the total resistance went down, whereas with a series circuit, the total resistance went up. But now we're going to group these two together to give us what's known as series parallel. So check this one out. We've got electrons coming down this way. We get to this node that's going to split up. So I'm going that way, so I'm going this way. So there's our parallel, but then this resistor up here is actually in series with the combination of those two. And that'll make a little bit more sense as we go through and start to pull these apart. Now there's another type of series parallel, and that's where we have these two in series. Then the combination of those two in series are then in parallel with this one. And so that's where our current will split up. So that's our parallel part. This one and that one, that's our series part. So how are we going to do these calculations? Well, it's got here, before we get into series parallel, just keep in the back of your mind that we are always looking to get the total resistance of the circuit first, and that's what we've been doing in previous lectures. So that is, we are looking to replace all resistors in the circuit, like that, with one single resistor, and that one single resistor will be such a value that it will give us exactly the same amount of current that we would have got originally with that circuit. Exactly the same. Same down here, whatever that current is there, that those two in parallel would have given us, we need to replace those two resistors with this one single resistor that gives us the same amount of current. We're going to be using that sort of convention with series parallel. So here is our first circuit. What color do I want? I want light blue. Now there's a bit of a process to get there. We're trying to get this first of all. One single resistor that gives us the same amount of total resistance as those three give us. But there's multiple stages to get to that point. Now what we want to do is we want to have a bit of a look at series parallel combinations. So we look at this one and go, well, okay, these two are in parallel with each other. And then those two put together are in series with this one. So it's a bit like a puzzle. The first step with this particular one would be, let's put those two in parallel with each other and replace those two with one single resistor. So to do that, we're going to have a circuit. Well, after we've done that, I should say, we're going to have a circuit that looks like this. We have our voltage applied, we have R1. Now this one single resistor is actually made up of these two. It's going to give us the same total resistance as these two would have given us. So in order to get that, we need to give it a name. In this case, I'm going to give it the name REQ, which is the equivalent resistance as what these two would have given us. So how do we do that? REQ equals, and let's just use product over sum for these two. So we're going to go 2K times 2K divided by 2K plus 2K. Pull out the calculator, and hopefully you can see these are, I mentioned I think in the previous lecture, that when you have two resistors in parallel that are exactly the same value, the overall result of that will be half one of those values. So let's test it out. 2K times 2K, and then divided by, and now we've got to put these in brackets here to make sure the answer is correct, divided by 2K plus 2K. There it is, 1K, which is half of 2K. So let's get rid of those two, replace it with a single resistor that is 1K ohm, and the overall resistance is exactly the same as those two in parallel. There we go. Okay, so get rid of those two, replace it with a single resistor of 1K, and the total current here will be the same as the total current here. But we're not quite where we want to be yet. The next step is to group these two. Now hopefully you can see that those two are in series with one another. So once we do this one, the circuit will look like this. We've got voltage applied, and then we're going to have a resistance here. I won't give that a name just yet. And by the way, I forgot to put the voltage applied here. The voltage applied here is 11 volts. And let's go back to blue. Now, how do we put resistors together in series? Well, in order to do that, and I'm going to give this a bit of a name, let's call it, well, it'd be RT now, wouldn't it? Because this is the total resistance. So RT is now the series combination of those two. So to get RT, it's simply going to be, and I forgot to write that value in, sorry about this, I'm jumping all around the place. It's going to be 1K plus 1K because they're in series with one another. 1K plus 1K equals 2K. I could do that on the calculator, but hopefully you guys can see that will be 2K. So that's it for getting total resistance. We needed to know, okay, let's get rid of those three, replace it with a single resistor that gives us exactly the same amount of total current. In this case, it will be a 2K resistor. So let's write that up here. RT equals 2K ohms. Now, what was the next step that we did after finding total resistance with any of our circuits, series or parallel? Well, the next step was finding IT. How much total current are we going to have now? Well, we work off this circuit because we've got two things about totals. We've got the total voltage, 11 volts, the total resistance, 2K. With those two, we can work out total current. So 11 volts divided by 2K equals, let's pull out the calculator, 11 volts divided by 2K, 5.5 negative 3, that's 5.5 milli. So the total current there is 5.5 milliamps. So therefore, if we just go up to this circuit here, the total current there will also be 5.5 milliamps. Because remember, the total resistance there is the same as the total resistance there. It's just that we're replacing it with one single resistor instead of using two. And then if we go back this way, the total current there before it splits up is also 5.5 milliamps. It splits up, however, to get some there and some there. It then regroups back together to again give us 5.5 milliamps. So there's whenever you're dealing with a series parallel circuit, you start with all of these put together in series parallel. You then try and find parallel or series combinations, whichever you can do first. In this case, the one we could do first is parallel. We then went to two resistors over here. Once we got to two resistors, we found, well, now those can go in series. We put those in series, and that's how we got to one resistor. We now have found the total resistance. With that, we could get the total current. Now we have to start going backwards, back to here, and then back to here. The reason we're going to go backwards is because we want to find out every single calculation we can in these circuits, including the amount of total current which we've got, the amount of current that way, the amount of current that way, and the amount of voltage across each of these components. So I'm going to stick with green. The next thing I want to find is, and we're going to go back this way, I want to know what is the voltage across R1, and well, the next one I'm going to do is what is the voltage across there. So what two things do we need to get voltage? In fact, I can even draw up the Ohm's law triangle right here. VIR. To get voltage, we need current and resistance. So to get the voltage of resistor 1, we need the current through R1, which is 5.5 milliamps going through there. Try and write a dot there. And what's the resistance of it? It's 1K. Pull out the calculator. 5.5 milliamps, negative 3 times 1K should be 5.5 volts. That's the voltage across R1, but now there's two ways that we could figure out the voltage here. We could do 11, take away 5.5 to leave us with that one, or we could do it the same way we did this one. So let's just do it that way. Let's go VREQ, which is our equivalent resistance here. The amount of current going through it, because it's a series circuit, is 5.5 milliamps, and it's also 1K. Therefore, it's also going to be 5.5 volts. Exactly the same as this R1. Okay, so now we've got these voltage drops. We then need to go back this way, because the last piece of the puzzle is, well, how much current splits up that way and how much current splits up that way? They're the last things we want to do. So let's get a different color here. Let's go purple. How much current goes through resistor 2? So we know we've got a total of 5.5 until we get to this point, and then it splits. So Ohm's law triangle, we want the current. What two things do we need to know? We need to know voltage, we need to know resistance. What is the voltage of R2? Well, remember that R2 was actually part of this REQ. The voltage across REQ was 5.5 volts. Now notice how R2 and R3 are in parallel with each other. What do you remember about voltage across components in parallel? Well, hopefully you remember that in parallel they all have the same voltage. Excuse me, I've got a very itchy nose tonight. So therefore the voltage across R2 is 5.5 volts. Now what we're trying to find here is current. So we need to divide it by the resistance of R2, which is 2K. Put it into our calculator. There's our 5.5 divided by 2K. And we get 2.75 to the negative 3, which is milli. 2.75 milliamps. So we start off with 5.5 going this way. We get to this node. 2.75 milliamps goes that way. There's a couple of ways we can figure out how much goes this way. We can either do 5.5, take away 2.75, and that's how much goes that way. Or we can do it the same way we did for the current through resistor 2. So let's do it that way. The current through resistor 3 equals, and we need to know everything about R3 to get that. We need to know the voltage of R3 divided by the resistance of R3. Remember that R3 was the second part of this equivalent parallel resistance. It has exactly the same voltage as R2 because it's connected in parallel with R2, which is 5.5 volts. So 5.5 volts divided by the resistance of R3, because we're trying to find current, remember. So we divide it by the resistance, which is also 2K. Exactly the same formula as this. It's also going to be 2.75 milliamps. Alright, so that's everything that we wanted to find from this circuit. Let's just go back here for, no, let's not go back there. Let's go to the circuit simulator, which is right here. Now, this was 11 volts, not 10. Let's check it out. We calculated that we would have 5.5 milliamps total. There's our 5.5, 5.5, 5.5. Now, what's going to happen when we get to this node right here? So it's going to split up. How much goes this way? 2.75, and that's what we calculated. How much goes this way? 2.75, just as we calculated. What's the voltage drop across these two? Or is it VD, 5.5 volts, and this is in parallel with it, it's also 5.5. 2.75, 2.75, you can see it's flowing into this node. So if we have 2.75 going into that node, another 2.75 going into that node, how much do we get coming out the other side? We're back to 5.5. So all of that resistance then goes into this 1K resistor there. What's the voltage drop across that? Well, it's 5.5, and that's what we calculated. Voltage drop of resistor 1 is 5.5, and then it continues on, 5.5 milliamps and 5.5 milliamps. So it all works out exactly as we thought it would. However, let's just double check this looking thing. Let's replace these two that were in parallel with a single resistor of 1K. Would we still have the same total current? And just to make things less confusing, let's get rid of those. There we go. There it is, still 5.5. The voltage drop across here, 5.5 volts, 5.5 volts. What if we went down to this one? Would we still get the same thing? Let's get rid of that. Connect that to there, replace that with a 2K resistor, Do we still have the same total current? Yes, we do, 5.5 milliamps. So then from there, we go back to that. We go back from there to there, and you can see total current exactly the same. Okay, now that was a bit of a process. First thing is we want to try and find the parallel resistors to put them together, and then once we've done that, put them in series, and that's how it worked for this particular circuit. Once we did that, we went all the way to our total resistance. From there, we found the total current, and then we had to backtrack on ourselves to start to figure out, well, what's the voltage of each of these? Once we know the voltage of each of those, we can now get the current through each of these. So that's it for this. It's quite a long tutorial. However, I did say a lot of words, so hopefully you guys picked it up. Download the notes as a PDF from your resources section, and see how you go with the quiz questions. Thank you very much for watching.